Every headline about the Western fire season is framing this as a drought story. It isn't. It's a design story about a suppression system built for a climate that no longer exists, now facing fuel conditions more extreme than the ones that produced every record-shattering megafire of the last 6 years. The Creek Fire's 50,000-foot pyrocumulonimbus, the Dixie Fire's 963,000 acres, the Oregon siege that burned 1 million acres in a week. Every single one ignited in fuels less dry than what 8 western states are reporting right now. In June, before the hottest months have arrived, and the fires those conditions produce, the ones that build their own thunderstorms, spawn their own tornadoes, generate their own lightning, cannot be suppressed by any tool the system currently possesses. If the fact that fire season started 6 weeks early got your attention, take a second and hit subscribe to Orbital View. We're tracking the Western fuel moisture data and the drought signals week by week as this season develops. Drop a comment and tell me, what are conditions like where you are right now? I read everyone. Here's what's coming. The West Snowpack Savings Account, the one that keeps forests alive through summer, just posted its lowest balance in the entire instrumental record, the single number in fire science that connects rising temperatures to burned acreage through a mechanism so direct it's almost mechanical, and why it responds on an exponential curve, not a straight line. A type of fire behavior that manufactures its own weather systems, spawns tornadoes inside its own smoke column, and cannot be suppressed by any tool humans currently possess. And the specific fuel moisture cliff, where living forests stop acting like vegetation and start acting like kindling. Let's get into it. Part 1. The conditions that started every record-breaking megafire. I need to walk you through what is happening across the American West right now in early June of 2026, because the data coming out of the monitoring networks over the past 8 weeks doesn't look like a bad fire season forming. It looks like the preconditions for something we haven't experienced in the modern record, and that claim, the worst fire season setup in modern Western history, isn't mine. It's coming from the people who write the federal outlooks, the people who've spent their entire careers watching these numbers. Start with the mountains, because that's where the story begins. Every winter, snow accumulates across the western ranges, the Rockies, the Cascades, the Sierra Nevada, the Wasatch, the Bitterroots. That snowpack is a savings account. It stores water through the cold months and releases it slowly through spring and summer, keeping soil saturated, vegetation hydrated, and forests too wet to burn. On April 1st of every year, hydrologists across the network take the most important measurement of the water year E, peak snow water equivalent, or SWE. Think of it as checking the balance in that savings account at the exact moment it should be at its highest, right before the slow drawdown of spring begins. On April 1st, 2026, that balance was the lowest ever recorded. Not low, not concerning. The lowest in the history of the measurement. Across the entire West, SWE came in roughly 65% below the 1991 to 2020 normal, the lowest since at least 1981, the farthest back Climate Central's analysis extends. The National Integrated Drought Information System, NIDIS, reported that 1,012 of 1,570 SNOTEL and snow course monitoring sites either tied or broke their all-time record lows. 64% of every single measuring station in the Western network hitting its floor simultaneously. And here's the part that made me go back and reread the report because I thought I was misunderstanding the units. Wyoming, Utah, Colorado, and New Mexico didn't just edge past their previous records. They obliterated them, 32 to 53% below their previous all-time lows. NIDIS used a phrase I've never seen in a federal drought product. No comparable years? The dataset contains nothing that looks like this. Arizona, Colorado, Idaho, Nevada, New Mexico, Oregon, Utah, and Wyoming. All 8 set state-level all-time records. California posted its second lowest at roughly 18% of normal. But California wasn't even close to the worst performer in the network. The reason the snowpack fell so far traces to a winter that barely functioned as winter. November through February, temperatures ranked among the warmest on record across the West, running 5 to 10 degrees Fahrenheit above the 20th century average. 8 western states logged either their warmest or second warmest water year from October 2025 through April 2026. And then came what I've started thinking of as the kill shot, a heat dome that parked itself over the Four Corners region around March 15th and sat there for roughly 10 days. Albuquerque hit 90 degrees Fahrenheit on March 21st. That is the earliest 90-degree day in the city's entire recorded history, more than 6 weeks ahead of normal. Las Vegas posted a March monthly average of 73.1 degrees. For context, that number is warmer than the city's long-term April average. This wasn't spring arriving early. This was summer arriving in March. The heat wave functioned as a snow eater. In parts of the Four Corners, it advanced melt-off 4 to 6 weeks ahead of the earliest previous dates on record. Whatever snow remained after the historically warm winter simply disappeared inside of 10 days. Jim Wallman saw it coming. A meteorologist at the National Interagency Fire Center and one of the co-authors of the Seasonal Outlook, Wallman had already flagged the trajectory back in early February. Talking to Capital Press on February 4th, he called the snowpack situation dismal. His exact words, "It's going to take a miracle March to get back close to normal." March arrived. It wasn't a miracle. So where does that leave us in June? As of June 2nd, the U.S. Drought Monitor showed 58.38% of the lower 48 in drought. Extreme to exceptional drought. Categories D3 and D4, the two worst levels on the scale, to some entrenched across the Mountain West. Fire activity nationally through the end of May had already reached roughly 2.4 million acres across more than 30,000 individual fires. By June 8th, the year-to-date total pushed past 2.5 million acres, running at approximately 195% of the 10-year average, nearly double. The National Preparedness Level, the federal government's readiness indicator for wildfire, sits at 2, with the Southwest Geographic Area Coordination Center elevated to Preparedness Level 3. Between 6 and 11 uncontained large fires burned through the first week of June, including a complex incident management team, deployment to the Seven Cabins fire in New Mexico. But the acres so far aren't the full story. The fire weather tells you more. NIFC's June 8th weather discussion flagged minimum relative humidity of 5 to 15% across Arizona, Utah, and Nevada, with southwest winds of 10 to 20 miles per hour, gusting to 35. The Storm Prediction Center placed roughly 147,000 square miles inside the Day 1 critical fire weather area for June 9th, close to 3 million people inside that boundary. Red flag warnings were active across dozens of fire weather zones in Colorado and Utah. Northern and southern Arizona, including the Phoenix metro, were under red flag conditions on June 6th when the city hit 105 degrees. Now the fuel data. The numbers that tell you not what the weather is doing today, but how ready the landscape underneath is to burn. And this is where I need you to lock onto the specifics, because they do enormous work. NIFC's June 1st, significant wildland fire. Potential outlook, put it in language that's remarkably blunt for a federal document. Great Basin fuels, near or exceeding record dry levels. Energy release. Component values, a key fire danger metric that I'll explain in full shortly, running 4 to 6 weeks ahead of normal across the southern and eastern Great Basin. In Northern California, ERC reached record daily values from May 20th through the 24th, approaching the annual 80th percentile. Northern California snowpack moisture was at 5% of normal, or less by May 26th. Southern California's 100-hour and 1,000-hour dead fuel moisture, the big logs, the deep litter, the material that feeds sustained burning, sat below normal through most of May. Live fuel moisture in Southern California had already fallen to mainly between 80 and 100%, with grass fully cured at lower elevations. Wallman, when the journal EOS pressed him on the seasonal outlook, gave an answer that sits at the exact center of this investigation. It's not necessarily a foregone conclusion that we're going to have a really busy season, he said, but everything is pointing that way. I'm going to hold that sentence through this entire video, because what follows is an investigation into what everything pointing that way actually means, what the physics says, what the historical record proves, and what happens to a landscape when these conditions converge. Part 2, the atmosphere's thirst and the exponential curve. There is a number in fire science, one variable, that does more work connecting climate change to the area that burns than any other single metric. Most people have never heard of it. Most wildfire coverage doesn't mention it. But once you understand what it measures and how it responds to warming, the entire modern wildfire crisis stops looking like a series of bad luck seasons and starts looking like a machine operating exactly as the physics predicts. Here's the concept, stripped to its core. At any given temperature, the air around you can hold a maximum amount of water vapor. Saturated air, completely full, can't draw any more moisture out of anything. But warm, dry air is hungry. Actively hungry, it pulls moisture from every surface it contacts. Every pine needle, every leaf, every twig, every dead branch on the forest floor, every blade of grass. The gap between what the air is actually holding and what it could hold at saturation is a measurable quantity. That gap is the atmosphere's thirst. Scientists call it vapor pressure deficit, VPD. Now, the physics that makes VPD so dangerous comes down to one principle, and it unlocks the entire story. Warmer air can hold dramatically more water vapor than cooler air. The relationship isn't gradual, it's exponential, governed by something called the Clausius-Clapeyron relation. So when temperatures rise, even if the actual amount of water in the air stays exactly the same, the gap between what the air holds and what it could hold widens. The thirst gets worse, and the atmosphere begins stripping moisture from vegetation faster, from soils faster, from every fuel on the landscape faster. Park Williams and John Abatsoglu published what I consider the foundational paper on this in 2016. Williams was at Columbia's Lamont Doherty Earth Observatory at the time. He's since moved to UCLA. Abatsoglu works out of UC Merced. Together, they quantified the connection in the proceedings of the National Academy of Sciences, and the answer was not subtle. Human-caused climate change accounted for roughly 55% of the observed increase in fuel aridity across western U.S. forests between 1979 and 2015. 55%. That isn't a marginal contribution buried in a list of factors. It's the majority. And when they translated that dryness into actual fire impact, the results stopped me flat. The extra aridity from warming alone contributed an additional 4.2 million hectares of forest fire area between 1984 and 2015, nearly doubling the forest fire area that would have burned without the human warming signal. But there's a second paper, and I want to be honest with you. This one is the finding I kept coming back to during this entire research process because of what it implies for the future. Huang and colleagues published in Geophysical Research Letters in 2022 and showed that in the forests of the western U.S., specifically the ones where dryness, not ignition, is what limits fire. Burned area doesn't just increase with VPD, it increases exponentially. The response isn't a line that tilts upward, it's a curve that steepens. Small increases in the atmosphere's thirst produce progressively larger jumps in burned area, driven almost entirely by the rapid growth of the biggest fires. The mechanism is essentially mechanical. Temperature rises, the atmosphere's capacity to hold water increases exponentially. VPD widens, fuels dry faster. Burned area climbs, and not at a steady rate. It climbs on a steepening curve. Every degree of warming produces more fire than the degree before it. And Yuang and colleagues, in 2021, closed the attribution loop. More than 2/3 of the observed summertime VPD increase across the western U.S. is directly attributable to human-caused warming, not ocean cycles, not natural variability, the warming signal. So when you look at the data from Part 1, ERC running 4 to 6 weeks ahead of historical curves, live fuel moisture dropping toward critical thresholds in early June rather than August. The atmosphere's thirst is the mechanism underneath. The air is drinking the West dry at a rate the ecosystems never evolved to handle. And that rate, because of the exponential physics, is accelerating. The question isn't whether VPD will drive more fire. That's settled science. The question is how much more and how fast. And to answer that, you need to understand how quickly these conditions can materialize, because the 2026 setup isn't just a product of years-long drought. There's a faster mechanism at work, and it catches the monitoring systems off guard. Part 3. Drought at the speed of a heat wave. There's a type of drought that doesn't creep in over seasons. It arrives fast, weeks, sometimes days, like a weather event wearing a drought's mask. And it catches the traditional monitoring tools flat-footed because those tools were built to track something that moves slowly. Picture a conventional drought as a slow leak in a bathtub drain. You notice the water level dropping over weeks and months. You have time to measure it, respond to it, plan around it. Now picture someone pulling the drain plug entirely. The water drops in real time. You can watch it go. That speed, the rate the water falls, not how low it gets, is what defines a phenomenon researchers call flash drought. Jason Otkin at the University of Wisconsin-Madison's Cooperative Institute for Meteorological Satellite Studies built the modern framework for understanding this. He and his colleagues established the formal definition in the Bulletin of the American Meteorological Society in 2018 dollars. And the definition is important because it centers on speed, not severity. Flash drought is, in their words, an unusually rapid onset drought. The rate of intensification is the diagnostic feature, not the endpoint. The term itself predates Otkin's framework. Mark Svoboda and colleagues at the National Drought Mitigation Center coined it back in 2002. But Otkin is the one who connected the dots between rapid onset and what happens to fire fuels downstream. The mechanism combines two forces at once. Precipitation falls below normal. Simultaneously, heat, wind, and low humidity drive what scientists call evaporative demand, the rate at which the atmosphere is pulling moisture out of soils and vegetation far above normal. When both forces converge, soil moisture and plant health can plummet below the 20th percentile in a matter of weeks. The 2012 U.S. flash drought is the textbook case. Vast areas of the Great Plains went from essentially no drought to extreme drought in weeks. Crops failed across the Corn Belt fast enough to overwhelm the drought monitor's weekly update cycle. But what matters for this investigation isn't the crop loss. It's what happens after the rapid onset phase. Otkin's research shows that the initial flash intensification sets up a longer duration drought that persists, and that persistence is what drives wildfire fuels past their ignition thresholds. He has drawn the link directly. In peer-reviewed work, he pointed to the 2021 Western fire season, the one that produced the Dixie Fire, which I'm going to walk you through in detail later, as a case where flash drought conditions through spring and early summer primed the landscape for the fires that followed. And here's where the monitoring gaps become dangerous. West of the Rockies, Edris and colleagues found that rapid intensification can happen even without triggering formal drought thresholds on the standard indices. The drought monitor is a weekly product built to track a slow phenomenon. Flash drought can blow through the window between updates. The system can catch it late, or underestimate the speed of deterioration while it's happening. The 2026 setup reads like a flash drought case study waiting to be written. Record snow drought removes the moisture buffer that normally keeps soils wet into early summer. The March heat wave delivers an enormous pulse of evaporative demand at exactly the moment snowmelt should be recharging the soil. The soil that should still be drinking from slow-melting snow is instead baking because the snow wasn't there. The vegetation that should be flushing with spring moisture is already stressed because the reserves were exhausted weeks ahead of schedule. I can't tell you yet, and I want to be honest about this, whether the formal flash drought diagnostics will capture 2026 at the speed the operational conditions suggest. That's a genuine uncertainty. But every ingredient is present, and they're present at intensities I haven't seen overlap before. When you combine the lowest snowpack ever recorded with one of the warmest winters on record, and a March heat wave that erased what little snow remained, the drawdown speed on soil moisture is essentially uncharted. And that speed matters because of where it leaves fuel moisture by the time the dry lightning season arrives. Because there's a threshold in fuel moisture science, a cliff, really? And what happens below it is what separates a manageable fire from an unstoppable one. Part 4. the 60% cliff, and the fuels that burn like kindling. Everything I've shown you, the savings account emptied to record lows, the atmosphere's thirst operating on an exponential curve, the flash drought compressing the drying timeline by weeks, all of it converges on a single measurable endpoint. Fuel moisture, because a forest doesn't ignite based on temperature alone, or drought alone, or wind alone. It ignites based on how much water is left in the wood, and there is a specific threshold below which the fire behavior changes categorically, not a gentle transition, a cliff. Living vegetation carries moisture the way your body carries water. A pine branch, a manzanita shrub, a chamise stand, they hold water as a percentage of their dry weight. Fire scientists measure this and call it live fuel moisture content. A reading of 100% means the plant is holding water equal to its own dry mass. Heavy, green, hard to ignite. 60% means it's carrying barely more than half. 40%, and it's practically a stick. The National Wildfire Coordinating Group publishes critical thresholds for different species, and these numbers are what fire behavior analysts across the West check every single day during fire season. Chamise, the dominant brush species across California's fire-prone coastal mountain ranges, crosses into critical territory around 60%. Manzanita hits its danger threshold near 80%. Sagebrush and conifers around 100. Gamble oak, a key species stretched across huge areas of the Mountain West, around 130. And what critical means in practice is something Abatsoglu has said plainly. Once live fuel moisture drops to around 60%, the living vegetation behaves and burns more like dead fuel. Those are his words. Think about the operational reality of that statement. The green forest, the living, growing biomass that's supposed to be the thing that slows fire, the thing that doesn't ignite easily, the thing that buys firefighters time, functionally becomes kindling. Dennison and colleagues quantified a related threshold near 79% for chamise in Los Angeles County, below which the probability of large fire occurrence jumped sharply. To see these numbers in practice, look at January 7, 2025, the day the Palisades and Eaton fires were burning in Los Angeles. Santa Barbara County's fuel sampling sites, Tapusquet, Harris Grade, Cachuma, Refugio, and West Gaviota, measured chamise at 61% live fuel moisture. The long-term average for that calendar date is 77%. The UCLA fire weather team reported that dead fuel moisture readings the same day ranked 6th lowest on record, and that was in January, the middle of California's supposed wet season. The fuels had crossed the cliff in the dead of winter. Now look at June 2026. NIFC's June 1st outlook reported that across Southern California, live fuel moisture had already fallen to mainly between 80 and 100% by late May. Grass at lower elevations, fully cured. Northern California's 100-hour and 1,000-hour dead fuel moisture categories, the ones that track the big stuff, the downed logs, the deep litter layer that feeds sustained, hours-long burning, ran below normal for much of May. And the Great Basin sat at what the outlook described, in unusually direct language for a federal product, as near or exceeding record dry levels. I want to be precise about what I know and what I don't. I cannot hand you a specific fire weather station in the Great Basin posting a single-digit dead fuel reading with a date stamp for June 2026. The public outlooks report in percentile ranges and regional summaries. That's a limitation of what's publicly available. But the trajectory fuels 4 to 6 weeks ahead of their historical drying curves, ERC at or near the 80th percentile in early June, live moisture already closing on the thresholds that preceded every catastrophic Western fire of the past 6 years. That trajectory is documented in federal data products, and it's unambiguous. Hold those numbers. 60% for the Chamise Cliff, 79 for the large fire jump, 80 to 100 for where Southern California sits right now. They come back hard when we get to the case studies, because every megafire I'm about to take you inside, the Creek Fire, the Oregon Labor Day Siege, the Dixie Fire, ignited when fuel moisture was at or near these exact thresholds. The difference is timing. In 2020 and 2021, fuels reached those thresholds in late August and September, peak fire season. In 2026, the landscape arrived there in June, And that early arrival doesn't just mean a longer fire season, it changes the kind of fire that becomes possible. Because when the landscape is this dry and the atmosphere is this unstable, fires don't just spread along the ground. They go vertical. They build towering convection columns that punch into the atmosphere. They generate their own wind fields, their own thunderstorms, their own lightning. And once a fire crosses that line, once it stops being pushed around by the atmosphere and starts dominating it, every tool in the suppression playbook becomes irrelevant. You can't fight a fire that makes its own weather. You can't outflank a fire that changes its own wind direction. You can only watch it, try to get people out of its path, and wait. The firefighting system that protects the American West was built for fires that stay on the ground. What comes next is fire in the third dimension. Part 5. Two kinds of monster. Most people, when they picture a wildfire, picture a thing on the ground. Flames running through brush. A line of orange moving across a hillside. Smoke rising. Firefighters cutting line ahead of the advancing front. And that picture is accurate for one kind of fire. There is another kind, and it operates by completely different rules. Fire behavior scientists at the National Wildfire Coordinating Group, the interagency body that writes the training manuals, formally distinguish between two modes, wind-driven fire and plume-dominated fire. The difference between them isn't a matter of degree, it's a difference in kind. And understanding that difference is essential to understanding why the current conditions across the West scare the people who study this for a living. A wind-driven fire does what the name suggests. The ambient wind, the weather moving through the region, pushes the fire in a direction. The convection column, the smoke and heat rising from the fire, tilts downwind. The fire advances in a roughly predictable direction at a roughly estimable speed. It's dangerous, it's destructive, and it can move fast. But it's fundamentally a two-dimensional phenomenon. The fire stays on the ground, the atmosphere pushes it, firefighters can get ahead of it, cut line, conduct burnout operations, anticipate where it's going. The 2018 Camp Fire in Paradise, California, the deadliest and most destructive wildfire in the state's modern history, was a wind-driven fire. The east wind pushed it downhill through a single drainage at terrifying speed. But the directionality was knowable. Plume-dominated fire is something else entirely. In a plume-dominated fire, the energy the fire itself releases overpowers the ambient wind. The convection column doesn't lean, it goes straight up. Vertical. A tower of superheated air punching into the atmosphere directly above the fire, sometimes reaching 40, 50, 60,000 feet. When fire behavior analysts at NWCG describe this in the S290 and S390 training courses, they call it fire in the third dimension. And they note, and this language comes from the official training materials, that true plume domination is a very rare event. It used to be rare. It isn't anymore. Here's what happens when a fire goes plume dominant, and this is the part I need you to hold, because it's the mechanism that makes the current fuel conditions so dangerous. The vertical column of superheated air creates its own wind field. Air rushes inward from all directions at the surface to feed the column, like a chimney pulling air from every side of a room. That means the fire's spread becomes erratic and multi-directional. It's no longer going where the wind pushes it, it's going everywhere the surface inflow pulls it. And the column, once established, reinforces itself. The more intensely the fire burns, the stronger the updraft, which pulls in more air, which feeds more oxygen to the fire, which burns more intensely. But the column doesn't just feed the fire. It builds weather. The superheated, moisture-laden air rising through that column can condense into towering clouds. Pyrocumulus when they stay below the freezing level, pyrocumulonimbus when they punch through it. A pyrocumulonimbus cloud, or pyro-CB, is functionally a thunderstorm created by the fire. It generates lightning, dry lightning, which can ignite new fires miles away. It generates downdrafts, powerful, turbulent bursts of air slamming back down to the surface, which can push the fire in directions no model predicted. And it generates extreme updrafts that make the airspace directly above the fire too dangerous for aircraft. Craig Clements at San Jose State University's Fire Weather Research Laboratory and Neil Leroux at the University of Nevada, Reno, have been at the forefront of measuring these events. Leroux and Clements published the first direct observational evidence in 2016 using scanning Doppler LiDAR and radiosondes during the Bald and Rocky fires, that the condensation level inside a pyrocumulus column can sit far above the ambient condensation level. The fire creates its own thermodynamic environment, and the NWCG training materials are explicit about one critical point. When fire behavior reaches the level of plume domination, torching, crowning, long-range spotting, fire-generated winds, it precludes methods of direct fire suppression. That's a direct quote from the national standard. Precludes, not complicates, not makes more difficult. Precludes. You cannot directly fight a plume-dominated fire. You can try to protect structures in its path. You can evacuate. You can wait for the weather or the fuel continuity to change, but you cannot suppress it. So the question hanging over the 2026 fire season isn't just how many fires will start. It's what kind of fires. When fuel moisture is this low, when the atmosphere is this unstable, when the atmosphere's thirst is this intense, the conditions that favor plume-dominated behavior are not just possible. They're baked in, and we know exactly what plume-dominated megafires look like in practice because we've lived through them. Twice. September of 2020. A fire ignites in the Sierra National Forest near Huntington Lake. Within 18 hours, it produces one of the largest pyrocumulonimbus events ever recorded in North America and spawns 2 tornadoes inside its own smoke column. The Creek Fire, and 600 miles to the north, on the same weekend, an east wind event drives 5 separate fires past 100,000 acres each across Oregon in 48 hours. That's where this investigation goes next. Into the fires themselves, into the specific measurements, into the minutes and hours when the suppression system met the physics, and the physics won. Part 6. When fire builds its own thunderstorm. And this is where the story takes a turn that most coverage of Western wildfire completely misses. Because everything I've laid out so far, the record dry fuels, the atmosphere's thirst, the flash drought compression suck, describes the conditions. The powder keg. What I haven't shown you yet is what happens when a spark lands in that keg under an atmosphere that's unstable enough to let the fire build something monstrous above itself. When a large fire burns through dry fuel, the heat it generates rises. That much is intuitive. But the scale of that rising air is something most people never grasp. A large wildfire can release energy at a rate measured in gigawatts, continuously for hours. The superheated air rockets upward in a column, and cooler air rushes in at the surface from every direction to replace it, like a chimney drawing from every corner of a house. If the atmosphere above is unstable, if temperatures drop off steeply with altitude, that rising column doesn't decelerate, it accelerates, it punches higher, and the moisture it carries, water vapor boiled out of burning vegetation, sucked in from the surrounding air, begins to condense. First, a cauliflower-shaped cloud sits directly atop the smoke column. Think of it as a thunderstorm embryo growing on a foundation of fire instead of solar heating. Fire scientists call that a pyrocumulus, distil, pyroq for short. If the column keeps climbing and ice crystals form at the top, it becomes something categorically worse. A pyrocumulonimbus, pyrocb, a full-scale thunderstorm, generated, powered, and sustained entirely by the fire beneath it. Neil Leroux at the University of Nevada, Reno, and Craig Clements at San Jose State's Fire Weather Research Laboratory published the first direct observational evidence of this process in 2016 in Atmospheric Chemistry and Physics. During the Bald and Rocky fires in Northern California, they deployed scanning Doppler LiDAR and radiosondes and demonstrated something remarkable. The condensation level inside the fire's convection column can sit far above the ambient level where a normal cloud would form. The fire creates its own thermodynamic environment, its own atmosphere within the atmosphere. What makes pyrocb so dangerous, and I keep returning to this as I track the 2026 fuel data, is the triple feedback loop. First, the powerful updraft in the column pulls surface air inward from all directions, creating unpredictable shifting winds that drive fire spread in ways no forecast model can reliably capture. Second, the thunderstorm generates downdrafts, powerful, turbulent pulses of air slamming earthward that can shove fire across containment lines in minutes. Third, the pyro-seed produces dry lightning, lightning with no accompanying rain. Each bolt can ignite a new fire miles from the original in fuels already sitting at their critical moisture threshold. David Peterson at the U.S. Naval Research Laboratory has tracked these events from above for years, following the smoke plumes that pyrocb thunderstorms inject into the stratosphere. He called pyrocb the fire-breathing dragon of clouds, and compared the largest events to volcanic eruptions in their ability to loft aerosols into the upper atmosphere, where they can circle the hemisphere for months. Peterson leads NASA's INSPIRE project with LaRoe as deputy principal investigator, and their work is trying to pin down exactly how large a role fire-generated thunderstorms play in the global climate system. That's how significant these events have become. They're being studied as a climate forcing, not just a fire hazard. And there's one final piece of the pyrocb puzzle that you need before we go into the case studies, because it shows up in the data I'm about to walk you through. LaRoe and colleagues published in the Bulletin of the American Meteorological Society in 2022 documenting fire-generated tornadic vortices, actual tornadoes born inside a fire's convective column, with rotational velocities reaching 30 meters per second, vortex depths extending to nearly 5 kilometers, and plume tops punching up to 16 kilometers. Those numbers are comparable to EF2+ tornadoes spawned by conventional supercell thunderstorms. Except these tornadoes are made of fire. The Instability Index fire behavior analysts use to assess the probability of plume-dominated events is called the Haynes Index. It combines mid-level atmospheric instability with mid-level dryness. Because it deliberately excludes surface wind speed as a parameter, the NWCG notes it's most effectively used for plume-dominated fires. Values of 5 and 6 on the scale signal significantly increased risk of extreme behavior, torching, crowning, and long-range spotting. Many practitioners now prefer the hot-dry windy index as a more complete tool, but the underlying physics is identical. When the air above a fire is dry and unstable, the fire can build a convective engine that the entire national suppression system cannot stop. And I realize this all sounds abstract. Convective columns, updraft velocities, condensation levels. So let me make it concrete with a single image. Imagine a campfire. Now imagine that campfire growing until it covers 1,000 acres. The heat from those 1,000 acres rises in a column of air moving at highway speeds, straight up, for miles, punching through the troposphere until ice forms at the top. The cloud that forms is indistinguishable from a severe thunderstorm on radar. It generates its own lightning, its own wind, its own rain, except the rain evaporates before it reaches the ground because the air below is so hot and dry. And every bolt of lightning that strikes the surrounding forest ignites a new fire and fuels that are already below their critical moisture threshold. That is a pyrocb event. And when I tell you that the current fuel conditions across the West are primed for this kind of behavior, I'm not speculating. I'm describing the exact atmospheric configuration, dry, unstable air over critically dry fuels that produce the most extreme pyrocb events in North American recorded history, both of which happened in the last 6 years. September 4th, 2020, the Sierra Nevada. The atmosphere is unstable, the fuels are at critical moisture, and a fire starts near Huntington Lake. Thoughts, Part 7, the Creek Fire and the night the Sierra spawned tornadoes. I've read a lot of fire case studies in the research for this channel. If you watched the Orbital View drought investigation earlier this year, the one that walked through the drought monitor data week by week, the Creek Fire is the case study that shows you what those drought numbers mean when they meet an ignition source. This is the fire that rewired how I think about what wildfire means in the 21st century. On the evening of September 4th, 2020, at approximately 6:45 Pacific Daylight Time, a fire ignited in the Sierra National Forest near Big Creek and Huntington Lake in the mountain country east of Fresno. The cause was never conclusively determined, but the fuel state was documented in extraordinary detail, and it was unlike anything the fire behavior analysts on scene had worked with before. The forest surrounding the ignition site had been devastated by bark beetle infestation during the preceding drought years. 80 to 90% of the trees in the immediate area were dead, standing columns of dry, resinous wood, many still upright but devoid of living tissue, their bark loosened, their wood cured by years of exposure. The forest floor beneath them was carpeted with fallen needles, branches, bark strips, and downed trunks. The living trees that remained were deep in drought stress, their live fuel moisture already well below seasonal norms. From the perspective of fire behavior modeling, the landscape presented fuel loading that was, and this is not hyperbole, off the scale that the standard fire behavior prediction models had been calibrated against. The models are built around typical forest fuel beds. This was not a typical fuel bed. This was a beetle-killed forest that had been air drying for years in a deepening drought, arranged vertically from litter layer to canopy in an unbroken ladder of combustible material. By the morning of September 5th, the fire had reached approximately 2,000 acres. By that afternoon, roughly 5,000. And then, sometime in the late afternoon and evening of September 5th, approximately 18 hours after ignition, the creek fire crossed a threshold that placed it in a category almost no fire in American history had entered. It built a pyrocumulonimbus cloud that reached approximately 50,000 feet. The GOES West geostationary satellite captured it in real time, and you can find that time lapse yourself. It's publicly archived. A massive anvil-top thunderstorm sitting directly over the Sierra Nevada, glowing orange from the fire beneath, its top flattening against the tropopause. It looks like footage of an atmospheric nuclear test, except it was made by a forest fire. The NASA aerosol index values from the smoke injection were among the highest ever recorded over the continental United States. And for context, the aerosol index is a satellite product that measures how much particulate matter a smoke plume is injecting into the atmosphere. High values mean the smoke is dense and it's being lofted high. The creek fire values didn't just set a high mark. They suggested the plume was punching smoke into the stratosphere, the layer of the atmosphere above where weather happens, at concentrations and altitudes normally associated with volcanic eruptions. Rodriguez, Leroux, Kingsmill, and Clements flew airborne cloud radar through the PyroCB and published the measurements in Geophysical Research Letters. I've read this paper 3 times, and the numbers still don't feel real. Updrafts of approximately 60 meters per second, roughly 135 miles per hour, directed straight up. Downdrafts of approximately 30 meters per second, nearly 70 miles per hour, slamming back down. Through a 3-kilometer deep layer, nearly 2 miles of vertical atmosphere, beneath a cloud top reaching the tropopause at about 12 kilometers. Their own description, dynamics, rivaling those in supercell thunderstorms. This wasn't a fire behaving badly. This was a fire that had become a weather system. And then the tornadoes. On September 5th, the creek fire spawned 2 fire-generated vortices. The first, near Huntington Lake, was rated EF2 on the enhanced Fujita scale, estimated winds of approximately 125 miles per hour. The second, near Mammoth Pool Reservoir, rated EF1 at roughly 100 miles per hour. The Mammoth Pool vortex tore through an area where hundreds of recreationists, campers, hikers, people who'd driven up for the long weekend were trapped. The roads in and out were burning. Visibility dropped to 0 in the smoke. The fire was in the canopy. The air was full of embers, and now a fire-generated tornado was rotating through the campground. Imagine you're one of those campers for a moment. You drove up to the reservoir on a September Friday for the last warm weekend. You parked. You set up camp. And now the sky is orange. The air is unbreathable. The only road out is blocked by fire, and the smoke column above you is spawning a tornado. There is no manual for this. There is no protocol for this. You are standing inside a fire that is making its own weather, and no one is coming by road. The California National Guard launched CH-47, Chinook and UH-60 Black Hawk helicopters on night vision rescue missions into the Mammoth Pool area. Military pilots flying on goggles through active fire smoke to extract civilians from an area where the fire was generating its own tornadoes. Several hundred people were airlifted out. The creek fire burned 379,895 acres before full containment on December 24, 2020, then the sixth largest fire in California history. Its plume-dominated behavior meant that its own downdrafts continuously fed oxygen back into the combustion zone, while pushing flames across containment lines that ground crews had spent days constructing. The column reinforced itself in a feedback loop. More intense burning drove a stronger updraft, which pulled in more surface air, which delivered more oxygen, which intensified the burning. The suppression system didn't fail from lack of effort. Thousands of personnel were committed. Aircraft were deployed until the pyro-CB turbulence made the airspace too dangerous to fly. The system met a fire that had crossed a physical boundary beyond which direct suppression is, in the NWCG's own language, precluded. And the fuel moisture at the time of the creek fire's ignition? It was less extreme than what NIFC is reporting across multiple western states right now. In June, before the hottest months have arrived. But 2020 didn't deliver just one mode of catastrophe. 600 miles to the north, on the very same weekend, the other kind of monster was about to tear through Oregon. Part 8. The Oregon Labor Day Siege and 5 megafires in 48 hours. On September 7, 2020, a weather pattern assembled over the Pacific Northwest that the state of Oregon's after-action report would later describe as without modern precedent. Normally, the prevailing flow in western Oregon moves from west to east, moist Pacific air pushing inland, keeping the western slopes of the Cascades green and damp. But in early September 2020, a high-pressure ridge built east of the Cascades, while a trough dropped offshore, creating a sharp pressure gradient that reversed the normal flow entirely. Hot, dry air from the interior, Great Basin poured westward through the mountain passes and funneled down through the river valleys of western Oregon, the Santiam Canyon, the Mackenzie River Valley, the North Umpqua Drainage, the Rogue Valley. The winds were extraordinary, and their duration was part of what made the event so destructive. This wasn't a brief gust. The east wind event sustained itself for roughly 36 to 48 hours, with damaging winds through the overnight hours when most people were asleep and when fire behavior is normally at its lowest. The Horse Creek RAWS, Remote Automated Weather Station, in the Willamette National Forest, recorded gusts of 66 miles per hour. That station sits in a river valley, not an exposed ridgetop. Timberline Lodge on Mount Hood, at elevation, clocked gusts exceeding 100 miles per hour. Portland International Airport recorded 52, the strongest September easterly gust in the airport's entire period of record. And riding those winds was air so dry it would have been notable in the Mojave Desert in August. Relative humidity across western Oregon, a region that normally sits in the 40s or 50s even in summer, collapsed into the high single digits and low teens. Some stations recorded 4 and 5%. NWS Portland's fire weather forecasters, in their area forecast discussion, used language that almost never appears in a Pacific Northwest product. They described what was happening as Southern California fire conditions, an atmospheric regime that Western Oregon's forests, its communities, and its emergency management plans were fundamentally not designed for. Between September 7th and 9th, roughly 48 hours, the wind event transformed existing small fires and drove new ignitions into a simultaneous conflagration across western Oregon on a scale the state had never experienced. 5 separate megafires each exceeded 100,000 acres. Lion's Head burned 204,469 acres. Beachy Creek, 193,573. Holiday Farm, 173,393. Riverside, 138,054. Archie Creek, 131,542. At the peak, more than 16 fires of 1,000 acres or more burned simultaneously across the state. The totals are staggering even for a state that has burned before. more than 1.2 million acres in roughly a week. 11 people killed, more than 4,000 homes destroyed. Some tallies run closer to 5,000 structures when outbuildings and commercial properties are counted. And the Alameda Fire, which ripped through the small communities of Talent and Phoenix in the Rogue Valley on September 8th, alone leveled more than 2,600 homes. These were not vacation cabins in the woods. These were neighborhoods, streets with sidewalks, schools, churches, grocery stores, gone. Foundations and chimneys standing in ash. Families received Level 3 evacuation orders, leave now, and had minutes to act. Some loaded cars and drove through smoke so thick they couldn't see the road. Some never received the orders at all because the cell towers, the phone lines, and the local emergency communication infrastructure were burning alongside everything else. The collapse of communication systems during simultaneous fire events is a failure mode that the emergency management community has studied extensively since 2020, and it still doesn't have a comprehensive solution. When the fire is everywhere at once, the systems designed to warn people about fire are consumed by it. Oregon State After Action Report called it the most destructive sequence of simultaneous wildfires in Oregon's history. That assessment wasn't contested. Nothing in the state's records approaches what happened between September 7th and 9th of 2020. And this was wind-driven fire throughout. The fires moved down slope and down valley at rates that exceeded evacuation plans designed around a fundamental assumption that you would have meaningful advance warning before fire reached populated areas. Now, the reason I'm presenting both the Creek Fire and the Oregon Siege together and spending this much time inside 2020Ds isn't to catalog two devastating events. It's to establish something essential about the thesis of this entire investigation. 2020 produced both catastrophic fire behavior modes in a single season. Plume-dominated in the Sierra, a fire that built its own thunderstorm and spawned tornadoes inside its convection column. Wind-driven in the Cascades, fires that ran down valley faster than the evacuation system could clear the roads. Both were driven by the same underlying conditions: extreme fuel dryness, critically low moisture, an atmosphere loaded with available energy. Both exceeded the physical capacity of the national suppression system. Both produced outcomes that the emergency planning documents, the county hazard mitigation plans, the community wildfire protection plans, the Forest Service land management frameworks had not contemplated and were not designed to survive. And 2020 didn't end there. California also produced the August Complex, which merged from multiple lightning-ignited fires into the first gigafire in the state's recorded history, exceeding 1 million acres. A 1 million-acre fire in California was a theoretical construct before 2020, something fire behavior professors mentioned to illustrate extremes. In September of that year, it happened. The season's damages across the West ran to roughly $16 billion, the third costliest wildfire year on record at the time. But the thing about 2020 that matters most for what I'm tracking in 2026 is that the West did not recover. There was no reset. No wet winter arrived to recharge the soils and rehydrate the fuels. The drought that fed those fires persisted through the following winter and deepened into 2021. The atmosphere's thirst, the VPD trend that Abatsoglou and Williams had quantified in peer-reviewed data, didn't pause or retreat. It kept climbing. And less than 10 months after the Creek Fire's pyrocumulonimbus lit up the GOES West satellite feed, a single tree fell onto a power line in Butte County, California, the same county where the Camp Fire killed 85 people in 2018. And the largest individual wildfire in the state's recorded history began from a single spark. Part 9, the Dixie Fire and 963,000 acres, July 13th, 2021, Feather River Canyon, near Cresta Dam, Butte County, California, the same county where the Camp Fire killed 85 people 3 years earlier. A tree falls into a Pacific Gas, an electric 12,000-volt distribution line. PG&E logs the outage. Crews are dispatched. They arrive roughly 10 hours later. By that evening, the fire covers 1 acre. 1 acre, a square roughly 209 feet on a side, the size of a football field, including the end zones. And from that single acre grew the largest single origin wildfire in recorded California history, a fire that would burn for more than 3 months, cross mountain ranges, erase communities, and cost more to fight than the Forest Service spent on every other fire in the region the year before. The growth was relentless, but not instantaneous. The first week, the Dixie Fire expanded to roughly 15,000 acres. Concerning, but not unprecedented. By July 21st, it passed 30,000. Then the conditions tightened. Record heat settled over Northern California. VPD spiked. The atmosphere became progressively more unstable, and the fire began to exhibit sustained plume-dominated behavior. Vertical convection columns, pyroconvective cloud development, erratic surface winds generated by its own updraft. By early August, it had crossed 100,000 acres. By mid-August, 400,000. It was growing at rates that exceeded the modeling, not because the models were wrong about the physics, but because the fuel conditions were outside the parameter space the models had been trained on. The Dixie Fire burned 963,309 acres before full containment on October 25, 2021. It was only the second largest California fire overall, behind the August complex, which was technically a merger of multiple lightning-ignited blazes and therefore not a single origin event. The Dixie was the first fire in recorded history to burn from one side of the Sierra Nevada to the other, across the crest of the mountain range. The conditions were essentially the culmination of every mechanism I've described in this investigation. 2021 was California's hottest summer on record. The state was embedded in the most extreme western megadrought in at least 1,200 years, a finding Park Williams and colleagues established using tree ring proxy data extending back to the year 800. The 2021 water year delivered Northern California less than half its normal precipitation. April 1st, Sierra snowpack measured 59% of average, with runoff reaching only 20%. The U.S. Forest Service took an extraordinary step. That September, one I cannot find precedent for, they closed every national forest in California to public entry, citing record-level fuel and fire conditions. The Incident Tracking System, INCIWeb, described the fuel environment in the Dixie Fire's path in plain operational language. Historically low fuel moisture, very dry, very receptive fuels. Those words come from incident commanders on the fire line, not researchers behind desks. The fire's behavior was plume-dominated from early in its growth, and the progression tells you exactly how that mode operates in practice. Smoke columns interacted with atmospheric moisture to generate pyroconvective clouds that spawned their own lightning and produced erratic, shifting surface winds. When a pyro-CB downdraft slammed back to Earth near the fire perimeter, it could push the fire in a completely new direction within minutes, a direction that no incident management team had planned for because no forecast model had predicted it. Spot fires ignited miles ahead of the main front, some through lofted embers carried aloft by the updraft and deposited downwind, others from pyro-CB generated dry lightning striking fuels so receptive they established immediately. Firefighters on the Dixie Fire described a recurring nightmare, finding new fires through breaks in the smoke that had already grown well beyond initial attack capacity. By the time crews could reach them, the new fires were already exhibiting their own extreme behavior. The fire didn't move in a line, it moved in pulses. It would push aggressively for hours, driven by its own convective energy, then pause when the atmospheric instability temporarily weakened or the fuel type changed, only to surge again when the next pulse of dry air or the next downdraft event reignited the cycle. The incident commanders described a fire that operated on its own schedule, indifferent to containment strategy. On August 4th, the Dixie Fire overran the town of Greenville. Greenville was a mountain community of roughly 1,000 people in Indian Valley, a town with a main street, a hardware store, a library, churches, homes that families had lived in for generations. The fire arrived from the west, driven by erratic pyro-CB generated winds, and moved through the town in a matter of hours. Firefighters who were in Greenville as the fire hit described structures igniting in rapid sequence. one after another, building to building, block to block. By morning, the commercial district was ash. Then Canyon Dam fell. Then Warner Valley. More than 1,300 structures were destroyed across the fire's footprint. One firefighter died of illness on the line on September 2nd, and the fire kept going across ridgelines, through river canyons, up and over the Sierra Crest, because it had crossed the threshold where human intervention becomes physically meaningless and only the weather or the exhaustion of fuel can end it. The cost captures the scale. Per Cal Fire and U.S. Forest Service figures, suppression of the Dixie Fire reached $637.4 million. Taylor, Harris, and Skinner at Penn State, publishing in Environmental Research Letters in 2022, confirmed it as the most expensive wildfire containment in California history. Their comparison is devastating. That single fire's suppression cost was almost double the entire amount spent by the Forest Service for fire suppression in its Pacific Southwest region the previous year. One fire, nearly twice the regional budget. More than 5,800 personnel were deployed to the Dixie Fire alone. 30 helicopters, hundreds of engines, dozers, hand crews, air tankers, every tool in the national cache. And here's the part that connects directly to the suppression system compound thread. The Dixie Fire was not burning in isolation. It was one of 108 fires that NIFC tracked simultaneously across 15 states during the summer of 2021. More than 2.4 million acres burned across the country at the same time. Resource orders went unfilled. Type 1 incident management teams, the highest trained, most capable teams in the system, were stretched across multiple assignments. The containment date on InciWeb read for weeks simply to be determined, because there is no containment date for a fire that controls the atmosphere above it. The smoke from the Dixie Fire didn't stay in Northern California. It degraded air quality across Nevada, Utah, and into Colorado. Satellite imagery showed the plume stretching hundreds of miles downwind, a brown-gray river of particulate matter flowing east across the Great Basin. And this was one fire's smoke, in a season with 107 others burning at the same time. So here's where the three case studies lock together and point directly at the thesis. The Creek Fire ignited in September of 2020 in fuels that had been drying through a drought summer. The Dixie Fire ignited in July of 2021 in the hottest California summer on record, in a megadrought 12 centuries deep. Both went plume-dominant. Both exceeded every suppression resource committed to them. The Oregon fires burned over 1 million acres in a single wind event. And the fuel conditions that existed at the time of those ignitions, the conditions that produced the Creek Fire's Pyro-CB, the Dixie Fire's 963,000 acre footprint, the Oregon Siege's 5 simultaneous megafires, are, by NIFC's own published data, less severe than the conditions the federal monitoring networks are documenting across the western United States right now. In June of 2026, 4 to 6 weeks ahead of normal dryness, fuels near or exceeding record levels in the Great Basin, live fuel moisture closing on the 60% cliff in Southern California, and the hottest, driest, most unstable months of the year still ahead. I don't know if 2026 will produce a Creek Fire or a Dixie Fire or an Oregon Siege. That's an honest uncertainty, and I won't pretend otherwise. The monsoon might arrive, a weather pattern might shift, but the physical preconditions, every single one of the ingredients that produce those fires, are present right now at magnitudes that match or exceed the historical analogs. The setup is more extreme. The only remaining variable is the spark. But fire conditions don't stay inside the fire perimeter. The 2026 setup isn't just a fire story. It's a compound story. Snow drought feeding into summer fuel desiccation, wildfire smoke crossing a continent as a public health emergency, and simultaneous megafires overwhelming the only suppression system the nation has. The chain starts where this investigation started, with the snow. Part 10, the chain that starts with snow. The fire story and the water story are the same story. Most coverage treats them as separate beats. Drought reports over here, wildfire reports over there, and maybe a line connecting the two if the editor remembers. But the mechanism linking them is direct, physical, measurable, and operating right now across the western United States at a scale that I haven't seen in any previous year's data. Snowpack is the West's water battery, and I don't mean that loosely. Hydrologists actually describe it that way. Snow accumulates in the high country through winter, stores water in frozen form through the cold months, and releases it as a slow melt through spring and summer. That gradual release does three critical things at once. It feeds rivers and fills reservoirs that supply drinking water and agriculture. It recharges soil moisture across millions of acres of forested land. And it keeps vegetation hydrated deep into the dry season, maintaining the fuel moisture levels that determine whether a forest resists fire or feeds it. When the battery is full, when April 1st snow water equivalent is at or above normal, the melt sustains soil moisture into July and August. The fuels stay wetter. The window for extreme fire behavior compresses into late summer. But when the battery is empty, and you now know what empty looks like, because the April 1st, 2026 SWE reading was the lowest ever recorded, the melt ends weeks early. Soils dry on an accelerated timeline, and the fuels cross their critical moisture thresholds in June instead of August or September. Craig Clements at San Jose State's Fire Weather Lab connected the chain explicitly. The snowpack being lower this time of year and melting out affects the soil moisture throughout the rest of the summer, which then affects the fuel moistures. Snow to soil to fuel to fire. Each link physical, each one measurable in real time through the SNOWTEL network, through soil moisture sensors, through the NFDRS stations that track fuel dryness. And the 2025 to 2026 hydrograph, the curve showing how much water flows through the system over the course of the year, tells you exactly how this chain is operating in practice. Because the winter was so warm, much of the precipitation that did fall came as rain rather than snow, or melted out of the existing snowpack during midwinter warm spells. That produced abnormally high early stream flow, water arriving in January and February when the reservoirs were already at seasonal capacity and couldn't use it, followed by a dramatically weak spring melt pulse. The hydrograph is flattening. The peak is lower and earlier. The summer tail is far drier than normal. For the Colorado River Basin, the water system that serves roughly 40 million people across 7 states, the numbers are sobering. April through July 2026, Lake Powell inflow is forecast at approximately 22% of average historical inflow. 22%. If that number holds through July, it could mark one of the driest years on record for the upper basin, and possibly the driest. The implications ripple far beyond wildfire. Into agriculture, municipal water supply, hydroelectric generation, interstate water compacts that were negotiated decades ago based on flow assumptions that no longer hold. But for this investigation, what matters is the soil moisture deficit those numbers represent across millions of acres of forested federal land between the headwaters and the reservoir. You can trace this deficit directly to the fire setup. When the spring melt is weak and early, the soils that normally stay saturated into June begin drying in April. The trees and shrubs that normally have access to subsurface moisture through summer start competing for a shrinking pool. And the atmospheric demand, the VPD, the thirst, keeps pulling from them regardless. There's a feedback loop at work here that makes it worse. As vegetation dries, it transpires less, releases less water vapor into the air. As transpiration drops, the local humidity drops. As humidity drops, VPD rises. As VPD rises, the remaining vegetation dries faster. The drying accelerates its own drying, drought feeding on itself. A University of Toronto study published in December of 2025 added a finding that connects the snow directly to fire severity. Longer snow-free durations, more weeks of bare ground between spring melt and the following winter's first lasting snow, correlate with increased extreme wildfire severity. The mechanism is intuitive once you see it. More time without snow cover means more cumulative drying. More drying means lower fuel moisture when peak fire weather arrives. And lower fuel moisture at peak fire weather means fires that more readily cross the threshold into plume-dominated behavior. One more compounding effect that you should know about. Low snowpack doesn't just feed fire, it shrinks the capacity to fight fire preventively. The safest window for prescribed burning depends on the snowmelt timeline. You need fuels that are damp enough to burn at low, controllable intensity, but dry enough to actually carry fire. When the snow melts early and fuels dry fast, that safe window contracts from weeks to days. The tool that could reduce fuel loading becomes harder to deploy exactly when it's most needed. More fire, less prevention capacity. The ratchet tightens. Thus, part 11, when smoke crosses a continent, the second compound thread takes the fire out of the western mountains and puts it in the lungs of people 1,000 miles away. And the scale of this, the geographic reach, the population exposed, the speed with which it overwhelms air quality systems designed for industrial pollution rather than wildfire smoke, is something that most Americans dramatically underestimate until they live through it. June 6th through 8th, 2023. You may remember this. Canada's wildfire season, which would become the most extreme in that country's recorded history, burning more than 18 million hectares, roughly 40 million acres, over 7 times the historical annual average pushed a massive smoke plume south, across the border and into the northeastern United States. More than 120,000 Canadians were evacuated, and then the smoke arrived in the northeast. On June 7th, 2023, New York City briefly became the most polluted major city on Earth. That assessment comes from monitoring data, not editorial judgment. A study published in the Annals of Emergency Medicine in 2024 by researchers at Montefiore Medical Center and the Albert Einstein College of Medicine quantified the exposure precisely. The daily mean concentration of PM2.5, a fine particulate matter small enough to penetrate deep into lung tissue and cross into the bloodstream, reached 203.9 micrograms per cubic meter. The U.S. daily ambient air quality standard is 35 micrograms. New York was running at roughly 6 times the legal limit. The air quality index hit 342. That's well into the hazardous category, the highest tier on the scale. The FAA issued ground stops and delays at LaGuardia and Newark because visibility had dropped below safe thresholds. Not from fog, not from a thunderstorm. From wildfire smoke that originated in Quebec, over 1,000 miles to the north. Major League Baseball postponed games. The Manhattan skyline vanished into an orange-brown murk that made midday look like a scene from a science fiction film. But the number from that day that stopped me during the research was from the 911 system. 754 respiratory-related calls. 14% of all emergency calls in the city, 1 in 7 calls was someone struggling to breathe, in excess of roughly 230 calls above the daily baseline. Emergency departments across the 5 boroughs logged spikes in CPAP usage and bronchodilator administration. And this was one day, in one city, from a smoke intrusion that lasted roughly 48 hours before the weather pattern shifted. I want you to hold those numbers against what a sustained Western pyro-CB season could deliver. June 7th was a single bad air day in New York from fires 1,000 miles away. A 2026 season with multiple simultaneous pyro-CB megafires across the West could produce weeks of degraded air quality across the interior and eastern United States. Not a single episode, but a recurring siege of smoke that the healthcare system would have to absorb on top of its normal summer caseload. Approximately 128 million people across the eastern United States were under air quality advisories during that June 2023 episode. And 2023 wasn't an anomalous single event followed by recovery. Nationally, that Canadian fire season reversed the long-running improvement in U.S. air quality that had been one of the Clean Air Act's signature achievements. National median PM2.5 concentrations reached their worst levels in roughly 15 years. Decades of air quality progress, the product of regulation, technology investment, and industrial transition, undone by fires that weren't even burning in the United States. Now connect this back to the pyro-CB mechanism from earlier in this investigation. When a fire generates a pyrocumulonimbus thunderstorm, the smoke doesn't just drift at low altitudes, where it dissipates over days. The powerful updraft injects particulate matter directly into the stratosphere, the stable atmospheric layer above where weather occurs, where it can persist for months and spread across an entire hemisphere. Peterson and Fromm at the Naval Research Laboratory tracked stratospheric smoke injections from the 2017 Pacific Northwest Pyro-CB events and the 2019 to 2020 Australian Black Summer events. The aerosol clouds circled their respective hemispheres. The Australian smoke was detectable in the stratosphere for over a year. At their most extreme, these fire-generated smoke plumes are not regional air quality problems. They are atmospheric forcing events with hemispheric reach. And the particles they carry, the PM2.5, aren't like industrial particulates that your body recognizes and your immune system tries to clear. Wildfire smoke contains a cocktail of organic compounds, metals, and ultrafine particles that are small enough to pass through lung tissue into the bloodstream. Chronic exposure is linked to respiratory disease, cardiovascular events, and in emerging research, gaze neurological effects. For children, the elderly, people with asthma or COPD, and anyone with pre-existing cardiovascular conditions, sustained exposure to wildfire smoke at the concentrations recorded in New York on June 7, 2023, poses a direct health risk. If the 2026 season produces pyro-CB megafires at the scale the current fuel conditions physically support, and I need to be precise here, this is a conditional statement, not a prediction. The smoke will not stay in the West. It will cross the Rockies, fill the Great Plains, and reach the eastern seaboard carrying PM2.5 at concentrations that the public health infrastructure of those regions was never designed or funded to manage. The monitoring networks that track air quality in the Northeast were built to detect industrial pollution, point source emissions from power plants, and factories that respond to regulation. Wildfire smoke arrives as an uncontrolled, diffuse, continent-spanning plume that no regulation can turn off. You can't issue a cease and desist to a pyro-CB event. Gacto. Part 12, when the suppression system meets its design limit. The third compound thread connects every fire to every other fire. Because the National Wildfire Suppression System is a shared resource, one pool of crews, aircraft, engines, incident management teams, and support infrastructure are, and when multiple megafires ignite simultaneously across different regions, that pool doesn't grow. It gets divided, and division past a certain point means triage. The system runs on a 5-step ladder. The National Multi-Agency Coordinating Group sets the national preparedness level, PL 1 through 5, based on current fire activity, fuel conditions, weather forecasts, and resource availability. At PL 1, things are quiet. At PL 5, the national resource pool is heavily committed, active geographic areas are implementing emergency measures, and regions without active fires are being stripped of standby resources to feed the ones that are burning. Think of an emergency room with a fixed number of beds and a fixed number of doctors. On a quiet Tuesday night, every patient gets immediate attention. On a mass casualty night, a multi-vehicle pileup, a building collapse, you triage. The beds don't multiply. The doctors don't clone themselves. You decide who gets care first, who can wait, and who has to be transferred somewhere else. That is what Preparedness Level 5 looks like for the National Wildfire Suppression System. And if you're a community near a newly reported fire, while the system is at PL 5, the response time isn't measured in hours. It can be measured in days. Because the Type 1 incident management teams, the most experienced, highest capability teams in the federal system, are already committed to fires burning in other states. The heavy air tankers are already flying other assignments. The hotshot crews are already cutting lines somewhere else. I want you to understand this not as an abstract organizational problem, but as a concrete life safety reality. When the suppression system is at capacity and a new fire starts in your county, the resources that would normally arrive within hours may not arrive at all. Your community's fire protection falls to whatever local resources exist. A volunteer department, a small rural engine company, maybe a state crew if one is available. Against a plume-dominated fire and record dry fuels, those resources are not sufficient. They were never designed to be. In 2020, the system hit that wall. The August complex, the Creek Fire, the Oregon megafires, and a simultaneous dry lightning siege across Northern California all demanded the highest level resources at the same time. Resource orders went partially filled or unfilled. Engines requested from the Northern Rockies were already committed to the Pacific Northwest. Air tanker availability dropped as the restricted airspace above multiple fires overlapped. In Oregon, the speed of the Labor Day fires meant that by the time resources could have been mobilized from other regions, the fires had already overrun the communities they were supposed to protect. The system's response time, which assumes a window between ignition and catastrophe, collapsed. 2021 was the same story with different geography. The Dixie Fire was one of 108 simultaneously tracked fires across 15 states. The Bootleg Fire in southern Oregon burned over 400,000 acres at the same time. The Caldor Fire threatened South Lake Tahoe. Resource sharing between fires became resource rationing. Each new assignment was a decision to pull from somewhere else. And this wasn't a failure of planning. It was a system encountering conditions beyond its design parameters in the same way that a bridge rated for 40 tons doesn't fail when a 60-ton truck drives onto it. It encounters a load it was never built for. The cost data traces the escalation. Federal suppression spending has exceeded $1 billion every year since 2011. Combined state and federal suppression peaked at roughly $4.4 billion in 2021. The Congressional Budget Office estimates average annual federal cost at approximately $2.5 billion in 2020 dollars for 2016 through 2020. And average annual acreage from 2017 through 2021 reached about 8 million acres, double the average from 1987 through 1991. The Department of Interior's wildland fire management budget climbed from $993 million in 2021 to $1.9 billion in 2025. Even at that level, the 2023 Wildland Fire Mitigation and Management Commission, the federal panel charged with assessing the national wildfire response, warned that the system was locked in a reactive and expensive cycle that consigns ourselves to an ever-increasing catalog of loss. The structural trap is mechanical, and once you see it, you can't unsee it. California's fire season is now roughly 105 days longer than it was in the 1970s. That extension keeps year-round firefighting crews locked in active suppression through fall and sometimes into December, shrinking the available window for prescribed fire and other prevention work to near zero during the months when conditions are suitable. Less prescribed fire means more fuel accumulation on the landscape. More fuel feeds larger, more intense fires the following year. Larger fires consume more suppression resources for longer. It's a treadmill accelerating under your feet while you're trying to run on it. And this is the part that connects directly to 2026. The suppression system enters this fire season already stretched thin from years of escalating demand, with prescribed fire backlogs growing rather than shrinking, and with fuel conditions across the West that are, by the federal government's own published data, more extreme at this point in the calendar than they were before either 2020 or 2021. If the season materializes the way the preconditions suggest it could, the system won't just be stressed. It will encounter the same kind of simultaneous, multi-geographic area demand that overwhelmed it twice in the last 6 years. Except the fuels are drier, the season started earlier, and the backlog of untreated acres is larger. As of early June 2026, the national preparedness level sits at 2. The Southwest GACC is at 3. Those numbers feel low given the fuel conditions. But the climb from PL2 to PL5 can happen in days if the trigger arrives: a dry lightning outbreak, a sustained wind event, multiple simultaneous ignitions across different coordination centers. It happened that fast in September of 2020, and every fire behavior metric suggests 2026 has more energy loaded into the system than 2020 did at the same point in the calendar. Part 13. The Arson Myth and the Ignition Misdirection. Every fire season, the same claim circulates. Most wildfires are started by arsonists. Crack down on arson, solve the fire problem. I've seen it in comment sections on this channel. I've seen it in news coverage. And the people asking deserve an answer grounded in the data rather than a dismissal. Jennifer Balch and colleagues published the most comprehensive analysis of U.S. wildfire ignitions in the Proceedings of the National Academy of Sciences in 2017. They examined 1.6 million wildfires from 1992 through 2012. The headline finding, approximately 84% of U.S. wildfires are human-caused. True, humans start the vast majority of fires, but arson is a minority of those human ignitions, gauge, and it's declining. The trend shows a decrease of roughly 15 fires per year from 1992 through 2020. The ignition categories that are growing are power line failures, equipment sparks, and vehicle-related ignitions. The Dixie Fire, a tree into a PG&E line. The Camp Fire, a PG&E transmission tower failure. These are infrastructure problems, not criminal ones. And the reason arson doesn't drive the burned area trend is a geographic and temporal mismatch that most people miss entirely. In the western forests, where the catastrophic megafires occur, lightning causes a minority of ignitions, but the majority of burned acreage, roughly 71 to 75% of area, burned in key forested ecosystems. Park Williams documented a nearly five-fold increase in western forest area consumed after lightning ignition between 1992 and 2015. Why do lightning fires burn so much more than human-caused fires? The answer connects directly back to the VPD mechanism. Dry lightning, electrical discharge from thunderstorms that produce little or no rain at the surface, occurs when the atmosphere is very dry at mid and low levels, but unstable enough to build convection at altitude. Those conditions, dry, warm, unstable doors, are the exact same conditions that produce high VPD and critically low fuel moisture. So lightning fires don't just start fires. They start fires in the precise atmospheric regime that favors extreme behavior. And they start them in remote, rugged terrain, mountain ridges, steep drainages, designated wilderness, where ground crews take hours or days to reach the ignition point and where heavy equipment access is limited or impossible. By the time suppression arrives, the fire may already be exhibiting the plume-dominated behavior that makes it unfightable. The driver isn't more arsonists. It's drier fuels, longer fire seasons, and more days when any ignition source, whether it's a deliberate act, a downed power line, a spark from a trailer chain dragging on pavement, or a dry lightning strike in a remote drainage, can produce a fire that crosses the plume-dominated threshold. The match matters for prevention policy. Absolutely. But the gasoline, the atmosphere's thirst, the record dry fuels, the extended fire window, determines whether that match produces a campfire or a catastrophe. And if you look at the 2026 setup through this lens, the ignition question almost becomes secondary. The landscape is so dry across such a vast area that the number of potential ignition sources on any given day, power lines, vehicles, equipment, lightning, campfires, cigarettes, is enormous. When every square mile of forest is at or near its critical fuel moisture threshold, you don't need an arsonist. You need a spark. Any spark. Yeah, part 14, the honest steelman for forest management. The second claim requires more care because it contains real science wrapped in political oversimplification. The claim, better forest management, thinning, logging, fuel reduction, would solve the wildfire crisis, and climate change is secondary or irrelevant. I'm going to give this claim the most honest treatment I can, because the places where it's right genuinely matter. Prescribed fireworks. Crystal Colden, a pyrogeographer at UC Merced, who has spent her career studying fire management and policy, calls it a vaccination for the land. During the 2021 Caldor Fire, which threatened South Lake Tahoe, prior fuel treatments in the Tahoe Basin are credited with slowing the fire's advance, enough to give the community time. Areas that had been treated burned at lower severity. Areas that hadn't were overrun. The evidence is real. Reducing ladder fuels, the material that carries fire from the forest floor into the canopy, demonstrably reduces fire intensity under moderate conditions. Prescribed burns reduce the total fuel available for wildfire. These aren't contested claims. They're established fire science backed by decades of field data. So where does the argument break? 3 places. Scale. Western prescribed fire acreage was flat or declining from 1998 through 2018. We're not doing more preventive burning. We're doing roughly the same or less while the area at risk grows every year. To put numbers on it, estimates vary, but multiple analyses suggest that somewhere between 20 and 40 million acres of western forest would benefit from some form of fuel treatment. Annual prescribed fire acreage in the West runs in the low single-digit millions at best, and much of that occurs in the Southeast, where fire ecology and conditions are fundamentally different. At current treatment rates, it would take decades to work through the backlog, and during those decades, the untreated acreage continues accumulating fuel. Liability concerns, the legal exposure that land managers face if a prescribed burn escapes, are a genuine barrier. Air quality regulations create windows where burning is prohibited even when conditions are otherwise suitable. The burn windows themselves are compressing as fuel curing arrives earlier each year. And the structural trap from Part 12, where suppression demands consume the same crews that would conduct prescribed burns, closes the loop. Getting prescribed fire to the scale that would materially change the Western fire trajectory requires a transformation in policy, liability law, and resource allocation that hasn't arrived. Limits under extreme conditions. This is the critical one for 2026 specifically. Fuel treatments work best outside extreme fire weather. Under moderate conditions, winds below 20 miles per hour, humidity above 15%, fuel moisture above critical thresholds, a treated buffer area can slow, redirect, or stop a fire. Those benefits are documented and real, but when a fire goes plume dominant, when it's generating 60 meter per second updrafts and lofting embers miles ahead of the main front, a thinned half-mile buffer is not going to stop it. The updraft doesn't care about stand density. The fire's own weather overwhelms the local fuel modification. The Creek Fire and the Dixie Fire both encountered areas where prior fuel treatment had occurred. Both fires went through them, not because the treatments were worthless. Under moderate conditions, those same treatments might have changed outcomes, but because the fire behavior had crossed into a regime where local fuel conditions were secondary to the fire's own atmospheric dynamics. The quantified science. Colden has been direct. We can't simply log our way out of our wildfire problem. So much is driven by climate change, particularly in the Northwest. Abatsoglou and Williams quantified the split. 55% of fuel aridity increase is from human-caused warming. Zhuang attributed more than two-thirds of the summertime VPD trend to the same cause. The physics isn't ambiguous. Warming raises VPD through basic thermodynamics. Higher VPD dries fuels. Drier fuels burn more. Earlier snowmelt extends the fire season. These are measured quantities, not modeling assumptions. The honest answer is that it's both, not either or. Both. And each factor amplifies the others in ways that make the compound worse than any factor alone. A century of aggressive fire suppression, putting out every fire as fast as possible, treating all fire as the enemy, left western forests with abnormally dense fuel loads. In forests that evolved with frequent low-intensity fire, decades of suppression allowed brush, small trees, and dead material to accumulate far beyond historical norms. That buildup is real, it's measurable, and it provides the fuel that makes modern fires larger and more intense. Expansion into the wildland-urban interface. The WI, the zone where development meets wildland vegetation, put tens of millions of people and structures directly in the path of fire. Between 1990 and 2010, the WI was the fastest growing land use type in the contiguous United States. More homes in fire-prone landscapes means more structures to defend, more evacuation routes to manage, and more ignition sources from human activity. The Camp Fire destroyed roughly 19,000 structures in Paradise, California. Those structures existed because people had built in a drainage with continuous fuel running uphill from the valley floor to the ridgetop. The fire did what fire does. It followed the fuel, and layered on top of both, the accumulated fuels and the expanding WI, human-caused climate change has accelerated fuel, drying through the VPD mechanism, extended the fire season by more than 3 months in some regions, and made plume-dominated behavior more probable whenever fires ignite. The three factors compound. Dense fuels burn hotter, Climate-driven dryness makes them burn more easily. More homes in the WUI mean more consequences when they do burn. And the suppression system, stretched to its limits, fighting the bigger fires produced by the compound, has less capacity to do the prescribed burning that would reduce the fuels for next year. Fuels management is necessary. I'll say it again because it's true and because dismissing it would be dishonest. Genuinely, demonstrably necessary, but it is not sufficient. Treating it as the complete solution, as the one lever that makes the problem go away, is a misdiagnosis that produces underinvestment in the interventions that would actually bend the curve. Both the fuel work and the emissions work need to happen simultaneously, at scale, and the data says we are not doing either at the scale required. So the evidence is assembled, the current conditions are documented in federal data products. The historical cases are established through 3 detailed investigations. The compound connections are traced: snow to fuel to fire, fire to smoke to public health, simultaneous fires to system collapse. The debunking is done. Now comes the part where I lay out what all of this means, where I give you the 3 honest interpretations of how this season could unfold, and where I'm straight with you about what I know, what I don't know, and where the uncertainty genuinely lives. Yet part 15, the case for manageable. I owe you something now. After 14 parts of evidence, the record snow drought, the atmosphere's thirst, the flash drought, the fuel moisture cliff, the Creek Fire's pyro-CB, the Oregon siege, the Dixie Fire's 963,000 acres, the compound connections from snow to smoke to suppression collapse, I owe you honesty about what the evidence does and doesn't prove. Because the 2026 fire season hasn't happened yet. It's June. The worst of it, if the worst comes, lies weeks or months ahead. And the difference between the worst fire season in modern Western history and a bad but survivable year could come down to a single weather pattern that hasn't formed yet. So I'm going to give you 3 interpretations, 3 ways to read the same data. I'm going to give each one its full weight, because the intellectually honest answer is that the evidence supports elements of all 3. Only the summer will sort them. The first interpretation is the most reassuring, and I need to present it as more than a token gesture, because it is grounded in real evidence and real operational precedent. Start with where the system stands right now. The national preparedness level, as of early June, sits at 2. The Southwest geographic area is elevated to 3. Those numbers are early. PL2 by late March is ahead of the typical curve, but they are not crisis numbers. The Type 1 incident management teams, the most capable response units in the federal system, are not yet deployed. Heavy air tankers are available and staged. The full weight of the national suppression system remains in reserve. That reserve exists for exactly the kind of season the preconditions suggest, and it has not been touched. The monsoon is the single most important variable that could change the trajectory. Every year, typically arriving in late June and strengthening through July, a large-scale shift in the atmospheric circulation pattern draws moisture northward from the Gulf of California and the eastern Pacific into the desert Southwest. When the monsoon arrives on time and at sufficient strength, it fundamentally alters fire danger across Arizona, New Mexico, and parts of Nevada, Utah, and Colorado. It wets fuels, it raises ambient humidity, it generates convective precipitation, real rain, on the ground in the fire zones. In strong monsoon years, the Southwest fire season effectively ends by mid-July, weeks before it would otherwise peak, and there are reasons to think moisture delivery could be better than the worst-case scenario suggests. AccuWeather's Brandon Buckingham has pointed to additional chances for appreciable rain from potential eastern Pacific tropical activity, an active tropical season in the eastern Pacific, even if no storms make direct U.S. landfall, can channel atmospheric moisture northward into the Southwest and Southern California through what forecasters call tropical moisture surges, pulses of deep tropical humidity that ride northward along the Gulf of California and produce widespread precipitation events across Arizona, New Mexico, and the lower Colorado Basin. A single strong surge can deliver an inch or more of rain across a broad area in 2 or 3 days. That kind of event doesn't just reduce fire danger temporarily, it can recharge soil moisture enough to shift the fuel drying trajectory for weeks. I should also note something that often gets lost in fire season coverage. Not every fire that starts becomes a megafire. In fact, the vast majority don't. The National Suppression System catches most fires in their first few acres. Initial attack, the rapid deployment of local resources in the first hours after detection, has a success rate above 95% in most years. The fires that escape initial attack and grow into the megafires I've been describing in this investigation are statistically outliers. They happen when fuel conditions, weather, and terrain align in specific ways, and while the 2026 setup makes those alignments more likely, it doesn't make them inevitable at every ignition point. Detection and response capabilities are also genuinely better than they were during the 2020 and 2021 sieges. VIAR satellite instruments provide higher resolution, more frequent fire detection passes than the MODIS sensors alone. The Pyrocast machine learning pipeline specifically forecasts pyro-CB potential, giving incident commanders advance warning of the atmospheric conditions most likely to push a fire across the plume-dominated threshold. Ground-based detection networks, camera systems, lookout towers, public reporting have expanded in many Western states since 2020. Early detection translates directly to faster initial attack, and faster initial attack is the single most effective intervention in the wildfire response chain. Fire season outlooks are probabilistic instruments, not prophecies. NIFC flags regions for above normal fire potential based on fuel conditions, drought status, and weather forecasts. That flagging does not mean every flagged region will burn. Some areas will receive localized rainfall from thunderstorms that the seasonal outlook couldn't resolve. Some will benefit from wind patterns that suppress fire weather for days or weeks. A broad area of elevated risk does not equal a broad area of realized fire, and there is historical precedent for outlooks that looked alarming and didn't fully materialize. Wallman's own language, not necessarily a foregone conclusion, reflects an experienced forecaster's awareness that the atmosphere is chaotic and that strong setups can be disrupted by pattern changes. A persistent trough digging into the Pacific Northwest, a stronger than forecast monsoon, a tropical moisture surge reaching further north than expected, any of these could change the fire calculus significantly in a matter of days. I am not dismissing this interpretation. It accounts for real capacity in the system, real weather variables that haven't resolved, and real improvements in the tools. If the monsoon arrives on time and no sustained multi-day dry lightning outbreak materializes across the Great Basin, 2026 could end as a bad season, worse than average, historically early deezer, without reaching the catastrophic threshold that the preconditions make physically possible. Part 16, the case. The published science makes the second interpretation is the one the weight of the peer-reviewed literature most directly supports. And it is, if I'm being honest about where I think the balance of evidence points, the one I find most persuasive, though I hold that assessment with open hands. The trend in Western wildfire is unambiguous, and it is not flattening. Burned area in Western forests has roughly doubled since the 1980s. The dominant driver, quantified by Abatsoglou and Williams with 55% attribution to human warming, is the VPD increase that makes fuels drier for longer. The exponential response curve, documented by Zhuang and colleagues, means each additional increment of warming produces more fire than the last. Not proportionally more, but disproportionately more, driven by the rapid growth of the largest fires. These are not contested findings on the margins of climate science. They represent the mainstream of published fire ecology and climate attribution. California's fire season is now approximately 105 days longer than it was in the 1970s. That's not a statistical artifact or a measurement problem. It's a physically measured extension of the calendar window during which fuels are dry enough and the atmosphere is unstable enough to support large fire growth. 105 more days of vulnerability. 105 more days when any ignition, a power line, a campfire, a lightning strike can become a disaster. The modeling work supports the trend line continuing forward, projections published in Communications. Earth and Environment in 2021 found a doubling of forest fire area for the period 2021 through 2050 compared to 1991 through 2020 under the assumption of constant fuel availability. The researchers tested whether fire fuel feedbacks, the idea that past fires consume fuel and thereby reduce future fire potential, would substantially attenuate the increase. The answer was only modestly. The climate-driven drying overwhelms the feedback. There is more fuel drying each year than fire is consuming. Under this interpretation, the 2026 setup is not an anomaly. It is the latest and most extreme expression of a trend that has been building for 4 decades. Record snow drought isn't bad luck. It's what the temperature record predicts when winter temperatures run 5 to 10 degrees above the 20th century average in a warming climate. ERC values 4 to 6 weeks ahead of normal aren't a monitoring glitch. They're what the VPD mechanism produces when the atmosphere's thirst operates on an exponential curve, and the snowpack that normally moderates the drying isn't there. This interpretation expects the 2026 season to be significantly worse than the 10-year average at Lowe's, and quite possibly worse than any individual year in the last decade. The range AccuWeather has projected, 5.5 to 8 million acres nationally, fits this framework. Paul Pastelok, their lead long-range expert, cautioned that expanding drought combined with heat, wind, and dry vegetation is a dangerous combination, and that conditions later this year could support any fires that ignite to spread faster, grow larger. That language is measured but unambiguous. Under interpretation 2, the suppression system faces serious regional strain, and this is the part that separates the intermediate case from the benign one. Specific areas, the Great Basin, Northern California, the eastern flanks of the Cascades, and the Sierra, the mountains of central Arizona, are likely to see fire activity that exceeds local and regional suppression capacity for sustained periods. National resources will be mobilized. The preparedness level will likely reach 3 or 4 nationally. Individual megafires producing plume-dominated behavior are probable, though the number and specific locations cannot be predicted. What does this mean for you if you live in the West? Under interpretation 2, the fire season is long, smoke exposure is repeated, and at least some communities will face evacuation orders. The system holds, it doesn't collapse, but it bends. The cost runs into the billions. The smoke crosses state lines, and the season becomes another data point demonstrating that the baseline has shifted permanently. If you live outside the West, interpretation 2 still reaches you through air quality. Sustained fire activity across the Great Basin and Northern California in July and August, even without catastrophic pyro-CB events, produces enough smoke volume to degrade air quality across the Intermountain West, the Northern Plains, and, depending on upper-level wind patterns, as far east as the Great Lakes and the Mid-Atlantic. The intermediate interpretation says this: 2026 is not a black swan. It's the trend. And the trend line is not flattening. It's steepening. Part 17, the case that keeps forecasters awake. The third interpretation is the physically possible worst case. I need to be precise about how I'm framing this. It is not a prediction. It is not a probability estimate. It is a scenario constructed from the specific evidence in this investigation that describes what happens if the variables resolve in the direction that the current preconditions point toward. If the monsoon fails to arrive, if persistent upper-level ridging locks over the interior west through July and into August, pinning the heat dome in place, suppressing precipitation, holding VPD at record levels week after week, if a dry lightning outbreak, a thunderstorm complex producing hundreds of electrical discharges without significant rainfall reaching the surface, sweeps across the Great Basin or Northern California during a period when the Haynes index is at 5 or 6 and the fuels are at or below critical moisture. Under those conditions, the landscape NIFC has described as near or exceeding record dry levels doesn't recover. It continues to desiccate fuels that are already running 4 to 6 weeks ahead of their historical drying curves, push further into uncharted territory. Live fuel moisture already approaching the 60% cliff in parts of Southern California, drops well below it across multiple states. And every dry lightning bolt that strikes that landscape has the potential to produce the kind of fire the Creek Fire and Dixie Fire demonstrated: plume-dominated, pyro-CB generating, and physically beyond suppression. Imagine you're an incident commander at the Southwest Geographic Area Coordination Center. The monsoon hasn't arrived. It's mid-July. Your fire weather forecaster has just briefed you on 3 new large fire reports in the last 48 hours. One in central Nevada, one in the Mendocino National Forest, one in the Uinta Wasatch Cache. All 3 are burning in fuels at or below critical moisture. The atmospheric profile supports pyro-CB development over all 3. You need a Type 1 team for the Nevada fire. The request comes back. The team is committed to an incident in Oregon that started 4 days ago and has already crossed 80,000 acres with 0% containment. The next available team is in the Northern Rockies and won't arrive for 36 hours. By the time it gets there, the fire will be 10 times larger. That is the suppression system compound connection made real. Multiple simultaneous megafires across different geographic areas, each demanding the highest level resources, each growing in fuels that support extreme behavior. The preparedness level climbs from 2 to 4 in days, then to 5. Resources held in reserve are deployed, then the reserves are empty. And the next fire that starts, the 4th, the 5th, the 6th, gets whatever local capacity exists. A rural engine company, a volunteer crew, against a fire building toward pyro-CB in fuels drier than what produced the Creek Fire's 50,000-foot smoke column. If this scenario materializes, the smoke compounds everything. Multiple pyro-CB events injecting particulate matter into the mid and upper troposphere simultaneously. Smoke flowing east across the Rockies on the prevailing westerlies. Not a single pulse like June 2023, but a sustained river of particulate matter fed by fires that burn for weeks. Air quality alerts in Denver, then Kansas City, then Chicago, then New York, the healthcare system absorbing a sustained, weeks-long burden of respiratory distress from populations with no experience of wildfire. Smoke exposure, no smoke filtration infrastructure in their homes, and no institutional playbook for managing PM 2.5 exposure at concentrations 6 to 10 times the daily standard. And the cost. Under Interpretation 3, the combined state and federal suppression bill could exceed the 2021 record of $4.4 billion. Insurance losses, property destruction, agricultural damage, healthcare costs, economic disruption from evacuations and road closures. The total economic impact would reach into the tens of billions. The communities that would bear the most direct burden are overwhelmingly rural, under-resourced, and located in the wildland-urban interface, where development has expanded into fire-adapted landscapes without the infrastructure to survive what those landscapes can produce. I don't think this is the most likely outcome. I've been straightforward about that through the entire investigation. The monsoon is a real and powerful weather feature. The suppression system has real unused capacity. The atmosphere is chaotic and capable of disrupting patterns. But the physical preconditions that would enable this scenario are documented in federal products right now. They are more extreme than the preconditions that preceded 2020 and 2021. And both of those years produced outcomes that no one in the system had planned for. The data doesn't tell you which interpretation is correct. What it tells you is what each one costs if it turns out to be right and you plan for one of the others. And there are specific signals that will tell you which way this is heading. If the monsoon arrives on schedule, if precipitable water values climb above 30 millimeters across Arizona by the first week of July, Interpretation 1 gains strength. If the drought monitor shows no improvement or further expansion of extreme to exceptional categories through June, and NIFC elevates the national preparedness level to 3 or 4, Interpretation 2 is tracking. And if a verified pyro-CB event occurs before August 1st, Interpretation 3 is no longer a scenario on paper, it's happening. Part 18, What We Know and What Comes Next. So, this is where I land after weeks with this data. The fire suppression system protecting the American West was built for a climate that no longer exists. The fuel conditions active right now across 8 western states are more severe, by the federal government's own published metrics, than the conditions that produced every record-breaking megafire of the last 6 years. And those megafires, when they crossed the plume-dominated threshold, were beyond the physical capacity of any human suppression effort. That's the thesis this investigation set out to test, and the evidence assembled across these 18 parts supports it. What is confirmed? The April 1st, 2026 snow water equivalent was the lowest in the instrumental record. Fuel dryness across the Great Basin is at or near record levels for the date. Energy release component values are running 4 to 6 weeks ahead of normal. National fire activity through early June is approximately double the 10-year average. VPD, the atmosphere's thirst, is the dominant climate-linked driver of western burned area, quantified at 55% of the fuel aridity increase, operating on an exponential response curve. Plume-dominated fire behavior, when it occurs, is beyond suppression capacity. And every megafire case study examined in this investigation ignited in fuel conditions less extreme than what is present across the West today. In June, what is uncertain, whether the monsoon arrives on time and at sufficient strength to meaningfully reduce fire danger in the Southwest. And sufficient is doing real work in that sentence, because a weak or delayed monsoon is almost as dangerous as an absent one. Whether persistent ridging holds through July and August, maintaining the heat dome over the interior West. Whether dry lightning outbreaks coincide with the window of peak fuel dryness. Whether simultaneous ignitions produce a multi-geographic area resource demand that overwhelms the national coordination system. The timing, location, and magnitude of individual fire events. And whether any specific fire crosses the plume-dominated threshold, which depends on the precise intersection of fuel state, atmospheric stability, mid-level moisture, and ignition timing in ways that no operational model can reliably predict more than 48 to 72 hours in advance. What is not uncertain, the direction, the trend, the physics, the mechanism connecting warming to VPD to fuel dryness to burned area is physical, quantified, and published. It is not going to reverse while temperatures continue to rise. The exponential response curve, documented by Huang and colleagues, is not going to flatten. The atmosphere's thirst, the VPD that Albatzoglu and Williams linked to 55% of the fuel aridity increase, is not easing. The fire seasons that emerge from these conditions will keep growing longer, burning more acreage, and testing a suppression system that was designed, funded, and staffed for a climate that the West has already left behind. One more distinction matters here, something I've tried to hold through this entire video. Uncertainty about outcomes is not the same as uncertainty about the mechanism. The mechanism is settled. Temperature drives VPD. VPD drives fuels. Dry fuels burn more. Snow drought extends the fire window. Plume-dominated fires, once they form, are beyond suppression. Every link in that chain is measured. What remains uncertain is the timing, the geography, and the scale of this season's specific events. That's meaningful uncertainty, the kind that determines whether 2026 becomes a 100-year fire season or merely a very bad one. But it's operational uncertainty, not scientific uncertainty. The science underneath is not in doubt. This investigation does not end with this video. It can't end here, because the data is still moving, and so will we. On this channel, we'll be tracking the NIFC Significant Wildland Fire Potential Outlook as it updates through summer, particularly the July and August revisions, which will incorporate monsoon observations and updated fuel assessments. We'll be watching the monsoon onset in real time, using the precipitable water values on the upper air soundings out of Tucson and Phoenix, the convective initiation patterns across the Mogollon Rim and the mountains of New Mexico, the Gulf of California moisture surges that feed the system. If the monsoon arrives strong, you'll hear about it here. If it fails, you'll hear about that too. We'll be monitoring the ERC percentile plots at key RAWS stations across the Great Basin and Northern California. The stations whose names fire weather forecasters recognize. tracking whether the 4 to 6 week ahead of normal signal persists, accelerates, or retreats. The GOES West satellite feed will be the early warning system for pyro-CB events. If a smoke column goes vertical, if a convective tower appears on the satellite imagery where no thunderstorm was forecast, that's the signal that a fire has crossed from a ground level emergency to an atmospheric phenomenon. And the VIRs and MODIS active fire products will track what's burning, where, and at what radiative power in near real time. And if a fire crosses the threshold, if a plume goes vertical, if a pyro-CB lights up the satellite, if the suppression system encounters the scenario that this investigation says is physically possible, we will be here with the specific measurements, the satellite products, and the analysis of what happened, why, and what it means for what comes after. I'll be watching the national preparedness level. If it climbs to 3 nationally, if the Southwest holds at 3 while the Great Basin elevates, interpretation 2 is tracking. If it reaches 4 or 5 before August 1st, interpretation 3 is underway. And I will be transparent with you about which interpretation the incoming data supports as the weeks pass. The Drought Monitor updates every Thursday. You can pull it up yourself at droughtmonitor.unl.edu. The NIFC Outlook updates monthly. The SPC fire weather outlooks are daily. And the ERC data at NFDRS stations near you is available through the